All right, let's go ahead and get started. Folks may be filtering in for a minute, but I want to make sure we get you to the posters on time. So we've got a very exciting group of presentations today. I'm Mike Fisher, I work at UNC, and Sarah here is a timekeeper. We've got Kyle taking notes. And we've got 4 wonderful presentations today, 2 relating to water quality in East Africa with a focus on fluoride in the first case, and also looking at microbial and other physical chemical parameters for our final presentation. We also have 2 presentations looking at toxic metals and water quality with generalizability or implications for a broader, potentially global scale. And I just do want to draw your attention to one correction in the program. I'll clarify later, but our final presentation beyond the label, assessing the quality of bottled water. Today we have Gloria from Jomo Kenyatta University of Agriculture and Technology, rather than the presenter and affiliation that were printed there. So just a quick correction there if you want to follow up. So I know folks will filter in, but without further ado, let's get started. We have a presentation on a field study about the performance of hydroxyapatite-based fluoride removal community filters in Ethiopia. So I'd like to welcome Lars Osterwalder from Acqua per la Vita.
Hi, good afternoon, everyone. Nice to be here. So my name is Lars. I'm a freelance wash consultant living in Addis, and today presenting on behalf of Acqua per la Vita. And it was all about learning more about how to sustain, improve, and possibly scale fluoride removal filters in Ethiopia. So just a little bit of background. There's millions of people in the East African Rift Valley that rely on drinking water with fluoride concentration above the WHO guideline of 1.5 milligram per liter. So dental fluorosis, skeletal fluorosis are really prevalent, and fluoride also a neurotoxin and impacting health development, child development. So since 2011, the Oromo Self-Help Organization, or Osho, started implementing community-level fluoride removal filters, initially using bone char, and since 2016, hydroxyapatite or HAP. So this field study was really about to assess how well those filters are doing. So I had the luck, or I was happy to be involved in this project a long time ago and could kind of come back, got some funding to have a colleague going and doing some field research. So between 2021 and 2023, we visited the 5 HAP-based community filters in East Jova Zone. So it's a total of 8 visits on a quarterly basis. During each monitoring visit, we checked the filter functionality, the fluoride levels, and the water consumption and tariffs. But we also checked microbiological quality and fluoride at the household level. So each time we visit one community filter, 10 random households within 1 kilometer radius around the community filter was visited. So 50 per monitoring round and a total of 400 throughout the study. The filter design for the 5 selected community filters, all the same, more or less. So a raw water storage tank going through 3 treatment tanks with each 1,000 kilogram of hydroxyapatite in series, going to treated water tank and then sold at the water kiosk. Just a few more information for context. So all filters were installed in relatively small community managed water points, supplying water from deep boreholes. Pumping was either with diesel generator, electricity from the grid, or solar system, and the fluoride concentrations were between 3 to 7 milligram per liter in the raw water. The 2G Dembel filter you see here was financed by Acqua per la Vita, the other 4 by the Oromia Regional Water Bureau. So let's look at some of the results. First, the water systems and the HAP filters were found not to always be running as we would wish for. So only one, the Furta system, we had both the water and the filter operating at the time of the visit. Roughly, we also had very different levels or consumption. Like in Langano, you can see it was just 0.4 cubic meter, 400 liters a day, while others were actually performing really well with up to 6,000 liters of water sold every day. The good news is the HAP filters perform pretty well. So here, example from Tucci Dembel, from 7 milligram of 7 milligram per liter in the raw water, it treated throughout the 2 years, well below the 1.5 milligram per liter. So changing those data a little bit and looking at the uptake capacity, so the gram per kilogram, so gram fluoride uptake per gram of filter media, you can see we reach around, what's that here, 6 gram per kilo, 4.5 gram once the outlet concentration is at 0.5 milligram per liter. Adding the other points, you can see it seems to be a bit consistent of how overall likely something around 6 gram per kilogram until we'd have breakthrough, or not a breakthrough, but we would have more than 1.5 milligram per liter in the treated water. Now an interesting finding is over here. So we looked at the different 3 treatment tanks. And we found that basically all the fluoride, which is the blue one, was removed in tank 1. Tank 1, probably something around 8 to 12. This actually was kind of going down again afterwards. 8 to 12 gram per kilogram until exceeding the 1.5 milligram per liter. A reason for that, we assume, is that there's a certain release of phosphate, possibly calcium, that then precipitates with the fluoride on the hydroxyapatite structure. But anyway, I think for design of the filter, optimizing design, that's really relevant because the material seems to expire over time anyway, as we have high fluoride coming through, even after tank 2 and 3, after a certain time. So, as discussed before, treated water was not always available. And even when water was available, not everyone was using it. In some communities, we found as few as 1 in 10 households having water without fluoride or with low fluoride concentration at home. Main reasons are unreliable opening hours of the water kiosks, its lack of awareness, and availability of alternative water sources, which may not be safe, but easier, more convenient to reach. And in one community, we had yard connections, which just makes it more convenient for households to access water, even when fluoride levels may be high. So other households might be using just raw water or alternative water sources instead. We looked at microbiological quality as well at the household level. So that's at the point of consumption, and found both whether the water is treated, untreated, or from other sources. Generally, the low risk category, so less than 1 colony forming unit of E. coli in 100 milliliter, was a small fraction. So that means that even so we have fluoride-free water and fluoride-safe water in this category or in this group here, only 11% actually had safe water available for consumption. We then installed inline fluoride chlorination system, the Clara system or the Acqua TAPS flow. I don't go into detail here. Again, some challenges with operating the systems we had, but at least in 15 households we could confirm that they are using the water and it had been chlorinated at the time of visit. And Sample size really small, but I would say as a first indicative conclusion, we can say yes, with chlorination, it is a bit better, and microbiological contamination overall is a big challenge at the household level. And just very briefly, not going into details here, we did a cost and revenue analysis for all the community filters. Here an example for the Tucci Dempal. So the overall revenue that you can see, that's on the revenue on the left-hand side, revenue of about 850 USD, mostly about 50% coming from the treated water. On the right-hand side, you can see the costs. You see already OPEX, or the operation expenditures, are consuming most of the revenue that the water committee has. So filter material costs that we estimated can only partially be covered. Filter construction costs are currently out of reach. Good. Some conclusion, or let's summarize. So we confirmed that the locally produced hydroxyapatite, or HAP, has indeed a high fluoride uptake capacity, likely about 8 to 12 milligram per gram under real-world conditions. However, we noticed that keeping the systems running is a challenge. And even when water is treated, not everyone is using it. And even if households are using the treated water, it may still not be safe for consumption. And finally, cost of the HAP is more expensive than current tariffs typically applied within the area. So a couple of recommendations. The findings show that the water service delivery model needs to be further refined. For example, through wash system strengthening activities at the district level and through business development support to WASHA. So fluoride removal should also always integrate microbiological treatment to a certain extent, because if the goal is to provide safe drinking water, we need to look at both fluoride and microbiological contamination. So more research is needed to see if HAP and how HAP can be regenerated to reduce the cost. And any engineer here in the room who gets excited about maybe working with us on improving filter design, really optimizing to reduce cost, please reach out after this session. So I'd like to conclude with a big thanks to Acqua per la Vita, funded the study, all the communities and the workers that supported doing this study, and it's really time to wrap up. So thanks a lot for listening.
I'll let you give you time for questions.
Any questions?
Yes, thank you. I'm Clara from PATH, and I'm an engineer. I'm curious if you have any data on how long it takes the water to make its way through all three filters, and whether that had any impact on the amount of time that water was available. And then if you have any data to support whether using only 2 tanks might only lead to increased water availability, but also reduce cost.
Thank you for the question. I think we see that here. I don't have the exact numbers available, but from the data we have, I would argue the uptake process is pretty fast. So already in the first tank with only 1,000 kilogram, as you can see here, basically removes all the fluoride. So the other 2 tanks are not actually required, and we would have gotten probably the same output with only a third of the material. To what extent further that could be reduced and minimized, I don't know, and we need to check with the team what data we have on the exact contact time. Thanks.
Last question, yeah.
And the last question, please.
If I understand correctly, the source of water is groundwater, right?
That's correct, yes.
So then I'm a bit surprised why the pathogen level is so high. Is there contamination, cross-contamination happening?
So the microbiological results are all at household level, point of consumption, so contamination during transport and storage. But with the chlorination, we'd expect to reach better outcomes also at the household level.
Thank you.
Thank you very much.
Thanks very much. So now we're moving to a talk with a broad focus on secondary data on a range of priority chemical contaminants. So Timothy Purvis from the Water Institute at UNC will be presenting work on an evidence map of toxic metal occurrence in drinking water in low and middle income countries.
You got applause.
All right, thank you everyone for joining. As Mike mentioned, I'm Timothy Purvis. I'll be presenting on behalf of a group of collaborators from here at the Water Institute at UNC, as well as collaborators from Rutgers University, Noguchi at University of Ghana East Legon campus, and University of Development Studies also in Ghana, on an evidence map of toxic metal occurrence in drinking water in low and middle income countries. This work is made possible due to funding from USAID through the GH-Pro program. So to give a bit of context, toxic metals, as the name implies, are those chemicals which are metals which can cause detrimental health outcomes. Each different toxic metal can have a wide variety of health outcomes that it can present, especially when looked at metal mixtures. But what I will be focusing on today is lead. Lead can cause significant issues, both for newborns and infants, where it can cause a stunting of cognitive development, as well as for adult populations with decreased cardiovascular output, increased risk of heart failure, and increased morbidity. We are seeing a growing focus on lead, especially in drinking water, over the course of a number of sessions that have happened here at the Water and Health Conference, which I recommend that you go back and watch some recordings of. And as we are looking at some of the evidence around the occurrence of these toxic metals in drinking water, we notice that there isn't great access to this evidence in a public setting, meaning that the public may not have adequate information on health risks posed by toxic metals in drinking water sources. Where there is evidence that is accessible, it's often not accompanied with adequate information about the instrumentation and the methodology that was used, meaning that we may not have reliable data being generated or data that we can verify. So we decided that we would do analysis of peer-reviewed studies to understand the distribution of these toxic metals in drinking water. To give a quick overview, a systematic evidence map, which is what we will be presenting, helps you understand the distribution of the data. We really wanted to, in our process, do a systematic evidence map to understand where there are gaps in that health-relevant data being collected globally. As a part of this, we'll be looking at the frequency of metals being studied, the type of laboratory equipment that's being used, and just general trends in global monitoring. Also, if no one here is a lab nerd like I am, I would like to give you up to speed on some of the terminology we'll be using. So first off, in the second column of this table, you'll see the WHO guideline value, which is essentially the limit above which you're going to see detrimental health outcomes at a population level. And what you will notice is the wide range of levels here. For cadmium, arsenic, and lead, we need to be measuring down below 10 part per billion, so at very trace levels in drinking water, to understand their relevance to health outcomes. Whereas for other indicators such as copper or sentinel metals like zinc and iron, we can measure at a much higher level and still have health relevant data. What this means is that if we want to measure things like cadmium, arsenic, or lead, we need to be using one of the gold standard methods, being ICP-MS, which is inductively coupled plasma mass spec. We can also use ICP-OES and GFAAS. All of these are capable of measuring down into the single digit part per billion level for these metals of interest. though ICP-MS is actually able to measure down much lower, and therefore it is the gold standard. However, with that, it is also more expensive. That also means that if we're looking at equipment like flame AES or colorimetry, which is less expensive, it's not actually as sensitive, and therefore it may not provide health relevant data at those low concentrations that we want to see, especially for lead. However, these types of equipment may be suitable for those sentinel metals and metals that have a higher WHO guideline value. So, to conduct our systematic evidence map, this fits in with a systematic review that is ongoing. If you'd like more information, I recommend that you watch Dr. Mike Fisher's presentation from Monday on the recordings, focusing on lead results. But first, we use machine learning to identify and do an initial screening of our data that came from PubMed, EBSCO, Global Health, and Web of Science. We were looking at peer-reviewed sources published in English in the last half century, where they were taking actual primary data measurements of drinking water samples for toxic metals in low and middle income countries. We looked at a wide variety of metals. At this stage in our systematic evidence map, we are including 2,000 studies. So of those 2,000 studies, we are seeing data from 87 different countries, which means there is still gaps in a lot of low and middle income countries. Across the data, we also have 8,751 pairs of adequate metal and method, meaning that you measured a metal with an adequate method, and therefore we will be able to analyze that data later on. We didn't see any change in the rate of equipment being used over time, which is very important because it indicates that we as a sector are not moving to use that gold standard ICP-MS globally, which may be due to the high capital cost of ICP-MS systems. There's also an increase in the rate of metals being studied over time, as you see here. However, this is somewhat skewed to a certain select set of countries. Additionally, there are some metals that are understudied, including some of our sentinel metals. So antimony, mercury, selenium, tin, and uranium are understudied, and that's largely due to the fact that they require that ICP-MS for sensitivity's sake. And so it indicates that there may not be adequate access to that instrumentation, which we'll explore. As I mentioned before, I will be focusing the rest of this on lead, as there is, as you just saw, over 8,000 data points that we have to do some analyzing of. We'll also be doing analysis at the SCG subregion, just so that you're familiar with the divisions of this. We'll be highlighting data from Latin America and the Caribbean, as well as Sub-Saharan Africa. Now, looking at results of metals by SCG subregion, we see very clearly that Southern Asia, which includes all the way from Iran over through to Bangladesh, makes up more than half of the data where we have adequate instrumentation for the metals that we are analyzing. Next up is Sub-Saharan Africa, and though it is second, is actually understudied in proportion to its global population share. Additionally, Latin America is also understudied, and so we will get into a bit of some of the reasons on that. So if we're looking at all metals, not just lead, but every time that we have a data point that we can use eventually in this study, we see a couple of trends. First of all, this list of 10 countries makes up roughly 60% of the data that we are getting, which means that we are very top heavy. There's not great coverage globally for toxic metal occurrence in drinking water. Additionally, there seems to be adequate instrumentation being used across this band from Turkey over through to China, which is interesting. A lot of our data is coming through there, as indicated by South Asia. In addition to that, we have these sub-regions or SCG regions where there are very few countries that make up the bulk of the evidence. So in Latin America and the Caribbean, Mexico and Brazil are making up more than 80% of the data that we have, meaning that the rest of Latin America and the Caribbean is very understudied. Similarly, if we look at Sub-Saharan Africa, 4 countries, namely Ghana, Nigeria, Ethiopia, and South Africa, make up more than 3/4 of the data that we have. The same holds true for lead, where Latin America and Sub-Saharan Africa also lack published data in the same kind of areas and regions. Now, if we look a little bit into the lab data and the instrumentation that is being used, this does make some sense. If we're looking at trace metal acceptable methods, so this first three columns, ICP-MS, ICP-OES, and GFAAS, we see that where we have access to adequate instrumentation, we are generating more lead data. This holds true for a lot of the other metals that were included in this study, just don't have time to go through all of them. And so the implication of this is in all of these other areas outside these islands where we have adequate instrumentation and data, we just don't necessarily have an understanding as to the health impacts posed by toxic metals. So the implication of that is that there is a notable gap in publicly accessible health relevant data on lead and a number of other toxic metals included in this study. We have islands of data in these large understudied areas across total continents, which requires that we increase monitoring in some way. That could either be an increase in investment that we have in actual laboratory equipment, or it could be increased collaboration between laboratories that have access to ICP-MS and communities that need to have their samples processed. And lastly, just to conclude, once again, there are these gaps in our data, and this is the largest known analysis of toxic metals in low and middle income countries. With that, there is additional analysis that will be ongoing. We will also be looking at some of the other metals of interest where we are seeing inadequate data and seeing if we can find any trends in that, as well as including high quality gray literature, which may supplement where we don't have adequate information from the peer-reviewed setting. We're also continuing with data extraction and interpretation, leading eventually to a systematic review. And we will eventually make this data accessible to the public via Tableau. So I want to leave you with one question, which is, if we know that our laboratory practices and policies aren't lining up with what is health relevant, then what can we do to actually move the needle and get adequate information? Thank you. I'd like to thank all of our collaborators once again here at UNC Chapel Hill, including some that are in the room, as well as those with our partner campuses over in Ghana. So thank you, everyone. I'd like to ask if there are any questions.
Mine was the most common source of this lead in drinking water. And second, what was the most common form of the lead that you found, that you saw in the drinking water? Like, was it more dissolved ion, was it more particle nature, or was it more bound to the organic surfaces?
Yeah, that's a great question. So in terms of the sources of lead, that will actually come at a later stage in the review. I would recommend that you go back and watch Mike Fisher's presentation, which went a little bit more in depth and may answer some of your questions. I can say though that we know that a lot of lead is coming from various sources, including the materials that we use in drinking water. Though I don't know if we finalized any of those results or if we hit a final conclusion on those. Additionally, I would say that we didn't actually look at dissolved versus particulate lead, though both, of course, pose significant health risks. Yeah, thank you. Other questions?
I'll ask one. Yeah, for those of us who aren't familiar with evidence maps, why is this a useful thing to do, right? So we got this whole other study where we talk about the concentrations, but why is this also relevant?
Yeah, an evidence map is incredibly useful as a tool to understand and kind of coordinate across a sector to see where we are doing a good job. So, for example, South Asia appears that we have a good saturation of data, and then to understand where we aren't doing a good job and potentially parse out why we aren't doing a good job. So that's part of what we eventually want to finalize in our conclusions of this, to see where there are gaps that could be solved by investment versus collaboration versus just policy-oriented solutions. Yeah, thank you.
Yeah, follow up on that.
Yes.
Like in larger country, maybe. I really don't know much about that, but I would assume that like in China and India, there are subnational evidence map that does the same thing as you just said.
Yes, and so I think that as we continue investigation, We will also ideally be looking for some of those countries that do have significant amount of data, being I think India, Bangladesh, and China. You may have the potential to then later on go and look at subregions. However, that would likely be at a later stage in our review, if I'm not mistaken, just based on how the data extraction is organized. But thank you.
All right. Well, thanks so much.
Thank you, everyone.
I think that's all the questions we have time for, but
Yeah.
you can catch Timothy right after the session at the break. All right, thanks so much. All right, next up we have another talk on lead and toxic metals, but this one is taking a mechanistic approach rather than sort of a secondary data approach. So Kyle Rezek from the Water Institute will be talking about assessing lead leaching potential of hand pump spouts and mechanized taps using NSF 61 test water.
Hello, everyone. Good afternoon. My name is Kyle Rezek, and I'm with the UNC Water Institute. And I'm here to talk about assessing lead leaching potential of hand pump spouts and mechanized taps using NSF 61 water. So, as we all know, groundwater is a very important resource around the world that's used by 1.5 billion people for drinking water. And it's especially useful for areas where surface water may not be as prominent, and in rural areas in sub-Saharan Africa, it's used by over 400 million people, and almost half of that is accessed using hand pumps. Hand pump corrosion, a large study was done back in the 80s, more focused on iron corrosion in hand pumps, and they did find that it was a large issue, and they did try to approach it with government standardization of hand pumps and regulatory compliance, though a lack of enforcement and actual compliance has been an issue in the past few decades. On the right is a map of showing the rural population percent for each country that are using either a borehole or protected well as their main drinking water supply. And a recent study done by UNC and World Vision found that lead present in hand pumps in 3 countries, in Ghana, Mali, and Niger, found that 82% of hand pumps had parts with lead content greater or equal to 0.25% of lead by weight percent. And then 9% of these water samples exceeded the WHO lead guideline of 10 parts per billion, or 10 micrograms per liter. So we wanted to determine what is causing the lead leaching in these water systems, and what parts specifically are the cause of these issues, that we could then determine what parts could be used as alternatives for replacing or for new water systems to reduce the amount of lead leaching into the system. So on the right is a picture of the India Mark II hand pump, and this is a very prominent hand pump used across the world. And manufacturers add a zinc coating from the hot dip zinc bath to protect the metal against corrosion by galvanization and to prevent corrosion. And the lead is added to the zinc bath because it's an alloying element to lower the zinc consumption and to lower the overall cost. The optimum amount used is 1 to 1.5%. So this was one of the items that we were testing. And though the whole schematic of the India Mark II hand pump has many different components, the tank and spout are the last liter where the water goes before consumption. So this was our determination of why this was to be tested in the lab, to see what the lead leaching would be. Another widely used component is the leaded brass tap, and lead is also an alloying element added to brass materials. And the reason why it's added in an optimal amount of 1 to 3% is it improves the machining of the part and also reduces leaks. I did some research, and lead-free, supposedly brass, does exist, but it's not widely used because of a high cost and low supply and not much demand. So this was also going to be tested in the lab, and usually the brass taps are connected to tap stands with mechanized boreholes, and these will be tested in the labs. I just want to make a note that World Vision, Ghana has switched to stainless steel taps, fortunately, in all new systems in Ghana. So stainless steel is a possible alternative to these galvanized or brass materials. So we have some spouts that were tested in the lab, as well as some taps that were also tested in the lab to see if these would leach lead in similar or hopefully dramatically lower results than the galvanized and brass materials. So the water corrosion chemistry is a large influence of how much of the lead in the material would leach into the drinking water. And there's many different factors that could contribute to that, but the three most important are the pH, alkalinity, and free chlorine in the system. And it has been found, many studies showed that increasing your pH and your alkalinity tend to have a lower lead leaching potential. And this can cause different effects, especially with climate change. If there's increased atmospheric carbon dioxide levels, that could potentially increase the groundwater acidity and maybe cause increased lead leaching due to the lower pH. So there have been international standards and certifications to try to limit the amount of lead leaching and to make sure that the parts that are being installed are safe to be used. NSF, the National Sanitation Foundation, is a large factor in this field, and they've developed NSF 61, which is a standard to make sure that there's a minimum health effect requirement that the products must meet. And there is a test which we carried out in the lab. That's a Section 9 protocol testing the last liter of water before consumption to see what the lead would be. There's also NSF 372, which tests the lead content, and that's if the certified products must meet less than or equal to 0.25% of lead by weight. And then the brass taps did have a British standard that allowed up to 4.5% of lead in the brass material, which I thought was surprising. So our key question was, how much can these leaded parts increase lead in the drinking water? And this was done by first using an XRF device to scan the materials to see what the lead percent content would be and to see whether it would be NSF 372 certified. We used NSF 61 with the different test water to determine the lead leaching potential with the dump and fill procedure, and then analyzing the results through an ICP-MS machine, as Timothy so wonderfully emphasized the importance of using in your lab testing. So the methods for this NSF 61 dump and fill protocol was, these were the items tested in the lab, and there is a set recipe for the synthetic test water that you use to dump and fill the components. This is a test that lasts 3 weeks, Monday through Friday, and you change the test water every 2 hours to simulate the stagnation over those 2 hours, as well as overnight and then over the weekend. And the daily samples are collected after the overnight and in the morning on Wednesday, Thursday, and Friday for those 3 weeks for all samples. PVC pipes were used as a control, since these were bought locally at a hardware store and were NSF 61 certified. So they were tested against the other components of taps and spouts to see if it would meet the certification as well. So our results from the XRF for NSF 372 showed that the brass taps, galvanized spouts would not meet NSF 372 certification because they had a lead weight percent greater than 0.25%, while the stainless steel taps had 0.01% of lead by weight percent, and then the stainless steel spouts and PVC pipes had less than limit of detection for lead by the XRF. Here are the results from the NSF 61 Section 9 protocol test, and as you can see, the stainless steel taps and spouts, as well as PVC pipes, some of the results, the minimum was lower than the limit of detection, and then it really wasn't too high, about 0.02 for the stainless steel taps. These are all parts per billion as well. And then the brass taps range from around 3.5 to 13. The galvanized spouts were from 3 to 42. And then the Q test statistic is used to determine the threshold, and if something is less than 1, it would meet the certification, and if it's above 1, it would not meet it. So here's a graph showing the concentration that is normalized throughout the 3-week period for each component. With galvanized spouts, you can see is, besides that one drop in the middle, is semi-consistent throughout the 3-week study, while the brass taps gradually decrease throughout the study, the 3 weeks. And then for both stainless steel products and the PVC, we're all very near zero or less than limit of detection, which is why they're all on top of that one line. So for some certifications for other recommendations, neither the brass taps or the galvanized spouts would meet the WHO guideline of the 10 micrograms per liter, or the FDA bottled water standard of 5 micrograms per liter, or the American Academy of Pediatrics, they have a recommendation of 1 microgram per liter. But the stainless steel products and the PVC pipes would meet that. So some implications is that some of these items that are sold in the supply chain are advertised as lead-free, though they could still exceed NSF 372 and leach lead into the drinking water. Though this is a very widely used international standard, NSF 61 is not an ideal method due to different issues such as rigorous protocol for the testing, which isn't able to be scaled down to the field as easily. The Q-test statistic is from a compromise, so between the industry and EPA, so it can be difficult to understand, and then there could also be background lead. This works for a general certification and an initial answer for more studies, but isn't a great answer for telling communities if their water is guaranteed safe from lead. This is just a global problem as well and not just focused on one area to keep in mind. So overall, the stainless steel components had the lowest lead along with the PVC pipes, so they would comply. Galvanized and brass should be avoided and would not comply. The next steps would be testing different components with Ghana's groundwater conditions for a more representative picture. And then these results can help inform policy decision-making regarding lead found in these parts and for future installation. I want to acknowledge and thank everyone at UNC and the Water Institute, World Vision for funding, different partners in Ghana for procuring the materials, and NSF and IAPMO for guidance on the methods and protocols. Thank you very much.
Does anyone have questions?
Yes.
Really great stuff. Thanks. I wonder if you could give us a little bit of context about the disadvantages of stainless components, maybe in terms of price, or I don't know if there are other factors, both the taps and the spouts.
No, sure. Thank you. Yeah, that's a good consideration when you're trying to implement that, what kind of drawbacks are with stainless steel. And definitely cost could be an issue, as well as we're seeing there possibly could be use of chromium in the use of the production of the stainless steel. So there may almost be a trade-off, but even if you could use the XRF to determine what may be in the material, it'd be a good guidance on whether or not you should install the products or see what they could contain.
Do you know like what the price differential is like? Is it like 5%? 80%?
I am not sure, but that is a good.
Frank can speak.
Ray knows.
May be able to answer that. We did a rough guesstimate, and to our surprise, which we haven't proved otherwise, it's about a 3% increase.
Okay.
It doesn't, I still don't understand it, and we've gone back to the numbers, and it keeps on telling us let's say certainly under 5%, but 3% is the number we've been getting.
Thank you for adding that. Yes.
Did you measure the concentration in water from brass taps?
Yes, they were measured. So after the dump and fill period, in the morning of the collection days, we dumped them into Nalgene bottles, and then that's where the samples were taken from.
How did they compare with from the hand pump? Because
In the field.
I mean, I wonder how much the tap influences the final concentration.
That is something that we're going to be looking into because we recognize that these components are not isolated and they're part of a whole system. So some future tests that we're planning is having additional components, whether it's stainless steel and brass, and how maybe galvanic corrosion could control and release different lead amounts. So it's definitely something to look into. So come back next year. Yes.
Let me just clarify for Rick that 3%, that's not 3% on the taps or just the component, it's the increase in our total budget for hardware supplies for installing a system.
Yeah.
Any other last questions?
I think we actually gotta move on to our.
Thank you, everyone.
Speaker. Thanks very much, Cal. Thanks, and I do encourage you to follow up with each of our presenters during the poster session. Next up, we have a correction in the program. So we will be hearing about an important and understudied topic of packaged drinking water. Our next presentation is Beyond the Label, Assessing the Quality of Bottled Drinking Water. However, and we apologize for this, there was a misprint in the presenter information. So we will be hearing from Gloria Magut at Jomo Kenyatta University of Agriculture and Technology. So please note that change and take it away.
Good afternoon, everyone. It's a pleasure to be here at UNC. And today I'll be talking about a topic that impacts us all, bottled drinking water. My presentation titled Beyond the Label, Assessing the Quality of Bottled Drinking Water aims to dive deeper into finding out the physical, chemical, and microbial quality of bottled drinking water sold in Embakasi Central, Nairobi, Kenya. My name is Gloria Magut. I'm an MSc student, a Master's in Public Health from Jomo Kenyatta University of Agriculture and Technology. So bottled drinking water is the fastest growing of seemingly safe drinking water. Globally, there's a growing reliance of bottled drinking water, yet little is known about the safety of water. There are primary drivers that lead to the demand of bottled drinking water, and these are better taste, better safety, compared to tap water, perceived health benefits, and distrust of municipal waste. There's an increase in production of packaged drinking water, yet little is known about the safety of this bottled drinking water. My study site was in Embakasi Central, Nairobi, Kenya. It lies in the southeast of Nairobi's capital. It is majorly a residential area with a population of around 185,000 people at the time of the study. So I chose this study area because in 2019, the Ministry of Health reported 65 diarrheal cases per 1,000 people in this area. And this was the highest rate of diarrheal diseases recorded in Nairobi. The media attributed this to the pervasive contamination of bottled drinking water, and therefore my study was set out to assess the physical quality, chemical quality, and microbial quality of bottled drinking water in this particular study area. We employed a cross-sectional study design, but first we did a scoping survey to identify the most commonly consumed brands. We employed lots quality assurance sampling method to enable us have the right quantity to assess the quality of water per brand. And for this, we used around 20 samples per brand. In total, we sampled 138 samples from 8 brands that were sampled from 38 mini-marts, 85 kiosks, and 35 street vendors. We got research permits that were got from Independent Scientific Review Committee and the National Scientific Committee. From our samples, we analyzed for pH, calcium, magnesium, lead, nitrate, sulfate, sodium, heterotrophic plate count, and E. coli. We employed membrane filtration method for microbial analysis, and we specifically tested for heterotrophic plate count, and E. coli. To ensure reliability and accuracy of our lab analysis, we first disinfected the laboratory and incubator surfaces using 5% sodium hypochlorite and 80% alcohol. We used incubators that were calibrated, that had calibration certificates, and were calibrated at 37 and 44 degrees Celsius. Every 10 samples was analyzed in duplicate, and each day would run a negative and a positive control. So we identified, for the microbial analysis, we identified E. coli and heterotrophic plate count based on color and morphology. For E. coli, we used sorbitol McConvey, and we identified the colonies with a pink color after incubation for 24 hours at 44 degrees Celsius. And for the heterotrophic plate count, we used nutrient agar that was incubated at 37 degrees Celsius after 24 hours of incubation. We then enumerated the results using colony forming unit per 100 millimeters of the tested sample. We did a physical analysis using an array of methods. Amongst them pH, we used pH meter, and for fluoride, we used colorimeter. So on to our results. The recommended specification for pH for packaged drinking water is 6.5 to 8.5. However, out of the 158 samples that were tested, we had 53 samples that had a pH of less than 6.5, and we had 6 samples that had a pH of more than 8.5. This indicates operational ineffectiveness in the treatment process. Other samples tested, which were calcium, magnesium, lead, nitrate, nitrite, sulfate, and sodium, were within the recommended threshold. On my table on my far right, we have a table that shows the percentage of samples exceeding the Kenyan guidelines. The exceedance ideally should be 0% because the Kenyan standards requires that there should be 0 growth of E. coli. However, looking from our table, we can find that all the brands, which were 158, had 12% exceedance. 12% of them were exceeding the Kenya guidelines, as you can see from our table. And we had brand 5, which had the highest level of exceedance with 30%. The graph on my left shows results of exceedance by brands, and this specifically is showing E. coli and fluoride. Looking at all brands, we have 13% of all samples exceeded the recommended threshold for fluoride, and we had 12% that of all these brands had 12% of them exceeded the threshold for E. coli. What is more worrying is brand 5, which showed that 100% of the samples had fluoride levels exceeding the required standards, the required national standards. And for the specific, again, brand 5, we find that 25% of the samples exceeded the safety threshold for E. coli. For brand 5, again, this brand was sampled, was packaged in this particular study area, and looking at the fluoride level, it shows that there is likelihood of fluoride in the bedrock. So what does this mean? This study recognizes the need to focus attention on aspects of drinking water. This is the role of bottled drinking water and the need to assess criteria such as quality across the source to the distribution to the selling point. This study also suggests that there is need for periodic audit of both bottled drinking water processing and packaging. This study also is of concern to policymakers because of the high fluoride levels that were seen in brand 5. This is because of the epidemiological and toxicological effects it has to the public health. This study provides evidence regarding the occurrence of physical and microbial violation among bottled drinking water in this study area, and this is just a snapshot situation of the market situation in Nairobi. This study also provides evidence of the potential risks of consuming bottled drinking water in this study area. And moving forward, there is need for further discussion about the quality of packaged drinking water and the need to enforce periodic auditing of these packaging plants. My recommendation to the policymakers is there is need for stringent operational monitoring of packaged drinking water. This means routine inspection of treatment processes, and there's also need to include fluoride testing in the water safety plan. The stakeholders is need for increased communication procedures and emergency response plans. And to the water packaging facilities, There's need to maintain a cold chain during storage and transportation. This is to ensure that the safety of water is maintained, because specifically for our brands, we would find that the brands were subjected to high temperatures, direct sunlight, and this was providing an optimum temperature for bacterial growth. There's also need to train employees in the water packaging plants on hygiene practices and the whole understanding of the treatment process. There's also need for implementation of standard operational procedures that will increase the effectiveness of the programs that during transportation and storage. I'd like to express my appreciation to my primary supervisors and to EAWAC who funded my project, and the different institutions that provided lab facilities for my work. And specifically, I would like to thank UNC for the travel scholarship. Thank you.
Really fascinating. So I was wondering if you looked at the difference in, the treatment types they purported to have, or whether they said it was, spring water or other things, to see if that affected E. coli and fluoride.
Yes, thank you for that question. So part of the data collection was to report on the treatment processes that were on the labels of this particular brands, and for specifically brand 5, it was reported to be doing reverse osmosis for the treatment process. Although we found fluoride levels, the ideal treatment process for fluoride treatment is reverse osmosis. Yet this brand showed to be doing reverse osmosis, so it shows that there's a breakdown in the treatment procedure for this particular brand.
Thank you for the very interesting presentation. I had a question. So Alistair Cohen at Virginia Tech. We're doing some similar research, and I was curious if did you look at all at variation within brands? Because it's one of the nice things about your study is you have such a large subsamples within your brands. I'm just curious how much the E. coli detects varied within some of the brands.
I didn't get your question. Please come up again.
Yeah, I'm sorry. So it's interesting and worrying to see the relatively high rates of detection for E. coli. And since you tested multiple samples from the same brands,
Yeah.
I was just curious how much that varied within each of the brands.
So that was outside the scope of my work, so I just did all the samples in a brand.
Okay, thank you.
So I think in Kenya, all products have nicely the Kenya Bureau of Standards label on it. So was this kind of very locally produced drinking water, or was it kind of more known brands with the KEBS label on it? And did you discuss it with the Kenya Bureau of Standards, your results? Because they should be very interested in that.
So out of the 8 brands, we have one brand particularly that is being distributed countrywide. And this brand also had elevated levels of E. coli and fluoride. No, E. coli, sorry. And these other brands were being sold in this particular area, but not all of them were being packaged in this particular area. And to the results, what next for my work? I plan to have an audience with policymakers to give them the situation of bottled drinking water in the country, and hopefully come up with a policy brief.
Yeah, thank you for a fascinating, if not disturbing study. So I remember many years ago, a study like this was done on beer in Egypt. And it was quite disturbing for all of us who used to work in Egypt. We stopped drinking Stella beer for a year. I'm going to be spending next month in Nairobi. Could you tell me what Can you divulge the safest water, the brand name of the safest water?
So part of the ethical approval is not to discuss the brand. Since I'm conscious of the safety, I can tell you the brands after this.
And that's a perfect segue. I'd invite everyone to engage with our presenters after the session as we go to our break. And thanks very much to all of our presenters. And thanks also to our timekeeper. And please join us for the
that's a lot.
I mean, honestly, I'm pretty sure at this point you're on the second most extractions at this point, I think. The competition between you and Claire.
She has to be.
So the hinge on it, for some metals, so it would be connected from the beginning.
And then here on Pat, the question about your future.
So,
This one to occurrence is
there's a lot.
Actually,
So we're going to do that. I have some students that
I think you mentioned your intro work. Well, no, I did not do that.
Needs to be out by myself. You need to know where those labs are. So there's like
Dangerous one.
Sarah, who is the timekeeper she's been on the study. It's legitimately over
Hi.
So,
That was amazing.
it is legitimately like 70
looking apparatus.
So they're like
So one of the things we're looking at is
so I think what will probably happen is we'll publish the like next study and then have some
let's say we have 3 participants testing it because of Vita.
I guess
Some of them went through, they're all contaminated, some either 9 or not, like, so that's one of the
Is that lab pictures that people are using stainless steel components, and then right next to the brass. So it's like the whole system.
Yeah, I think it's good. So you already know what that is.
Oh, okay, great.
Stainless steel next to a what?
The brass, there's the brass. We have
Areas
like you had 0% and then brass on
That brand.
so it's like
And here we would say that if there was one
The type of equipment they used or the
actually there might be, but it's
We've seen the spring water, like also the water source, and we see this. So our studies
that's a huge problem.
didn't see it until California.
I think that
is some stainless steel better than
you know, it'd be lovely if it was just like
QMS is that on brass.
Yeah, I'm not an expert, but I would be more interested in if you're interested in the exact the flowing water test for the tree, you know, a couple seconds.
I recommend because there's paper.
I didn't work regularly.
Once you continue throughout the day, so yeah, that's what you're suggesting.
That would be a great
Tested a bunch of alternative if you don't have all the drawbacks on them.
Well, anyway, we're saying
Parts or usually a discussion about this. It's a shame that we might get a.
Thank you for the question.
Have to give it a minute.
Did you have a question?
No, ICPMS is the only way to make final health decision. Tools are proven. One thing for it to work in a lab, synthetic wall. So it's like they're like participants.
Maybe it's
You still have things are gonna go wrong.
I'm just curious.
Because of that, like a lack of validated.
What am I supposed to do?
He currently has some work on
It's regulated. Because like in the US, it's like it's like picking two definition of it does, but then it's like
It's actually fine.
That's what we're doing.
And that, so
You're actually on. It's like the only exception. No. Thank you.
Yeah, that's what we were just talking about.
in the document, if it says something like this, you know, people evidence.
Yeah, keep quiet.
Times are tonight or weekend.
So what you're saying?
Onyesha your level. You are not at that
Example, we're working in the lab right now, and all they have is an UES option from Vita. Like, well, I just want to shift this.
Yeah, that's the
So,
Yeah, brass and you just flush it. It's not good.
Because when I went to the
Your chain campaign.
detection.
Issue two,
and they
You said there was one thing where you
That's the other thing.
it's been like being packaged.
It's such a long,
Somewhat access.
After you're 17 times island.
Sana wakati lifestyle. Yes, we use that.
I love how we manage because an ideal
it shows high lead.
Maybe, but
So it's not a,
easier to have where they're leaking a little bit. How long does it like dripping? Like what?
I see him as
What are the
yes, GFAPS.
What they're still moving.
Is I think
that's on
public health magazine. When we do the full extractions and I think that adds dripping somewhere. Actually, things that the later stages of analysis to at this point, it's not. That's just because recommendations. Yeah, of course. Thank you.
It's easier to say like, sorry, your pipe is leaking. It's just on purpose. I want to ask you to flash very previous water. Maybe they're super bad answer. Never flash because it's so precious. Or they would have to put it back in the system.
Yeah, so you can also. Thanks, man. Yeah, I need to get my
Yeah, anyway, just the black one. I'm very glad you're doing this. We feel like we're a lot of water.
If it's possible, I also want to have you analyze it.
Oh, yeah, I can send that over. I'll give you, do you have a business card?
And then one more thing is
Okay, yeah.
Well, you finally got a name tag. We need. Finally got your name tag.
there are,
It is an issue, and I hope you agree, this is an issue.
Okay.
Let's solve this.
So it's tidal water reliance on bottled water.
Alistair's question is, there were any way to review brands that were
If you can't access it, let me know.
there was like, yes, brand two.
Hard, okay. That's why we're solving it.
Very bad
Thank
reading.
you. I like that, that's very nice.
There's no trend to be, there's
What is your role?
I can just tell you my email address.
It's random and sporadic.
I don't have any changes.
Quality control.
Very important. Well, thank you for.
I really think it's about
It's important work. And thank you, yeah, again, to World Vision, because they're supporting us. So it helps that research and it helps you all out. Again, seeing your field. Yes, thank you.
I'm sorry, so I think it's more time.
Oh, okay. That's what I was very excited to see.
What else can we optimize? I love optimizing.
That's the fun part of this conference. Yeah. Oh, yeah, I'd be happy to chat about that. Maybe we could find a way to collaborate on that. Yeah. Oh, sure. Yeah. Okay, yeah. Happy to. Yeah, please.
Yeah, that's what we're
meeting with somebody at 4:30.
right now. It's Brussels.
Yeah, of course.
But I'm
But in reality, the tap is connected to a tank, storage, and that